Learning quantum field theory can be a challenging journey, but with the right approach it becomes much more manageable. Today we are delving into a topic that both fascinates and challenges aspiring physicists and curious minds alike: how to learn quantum field theory. This is in continuation of my earlier video, and today we are going to discuss how to learn quantum field theory effectively, including the methods, study approach and recommended books that will help you grasp this complex but rewarding subject. My name is Shaunak and you are watching this video on my channel Physics for Students. Welcome to the second part of how to learn quantum field theory. For those who have missed my earlier videos, I am putting up a link in the I button, but it is important to just make a quick whirlpool tour into what are the important topics that we have covered in the last video. So here is a quick review. First, we have seen that quantum field theory is an assimilation of three important theories: classical field theory, special relativity and quantum mechanics. Together it makes up the quantum field theory. Quantum field theory treats particles as excited states, which is on a higher energy than the ground state. It uses the equation of motion by minimizing the Lagrangian, and the important Feynman diagrams actually gives the representation of the subatomic realm, the creation and annihilation operators, and so on. We have also seen in the earlier video that why do we need a unified theory. I'm not elaborating, I'm putting it in the I button. Please go ahead and check it, it will be important for you. We have also dealt that why it is difficult. We know that quantum field theory is difficult. I have enumerated the reason that it embraces a wide field of physics which includes classical mechanics, relativity, statistical mechanics, electromagnetism and a lot. And because it is relativistic in nature, so we have to include all the equations of special theory of relativity into this. We have also seen that it leads to interactions of particles, which actually makes the calculation much more challenging, and it includes various degrees of infinities, which are technically termed as a renormalization, which also makes the concept very challenging. And there are certain conceptual challenges which includes vacuum fluctuations and other interpretations of virtual particles. So this was basically the reason why we call it as difficult. Now we have also seen that there is a concept which is called a perturbative and a non-perturbative quantum mechanics, and the quantum mechanics which we use generally is using the perturbative method in order to describe a very complicated quantum system. If we talk of quantum field theory, it is both perturbative and non-perturbative. At low energies we know it is perturbative, but in certain high energies it has to be non-perturbative, and that is why the challenges rise that we have to go beyond the perturbation theory, which is otherwise easy to interpret a quantum system, but to obtain certain things which are meaningful results. Now you understand, with so much amount of complex calculation, infinities and degrees of freedom, it becomes very challenging for quantum field theory if you're approaching a non-perturbative method. So non-perturbative quantum field theory is a developing subject which has not yet been finalized, and there are certain methods and there is a degree of difficulties because there is no single approach to this particular method of dealing QFT. And these are the methods we have not dealt in detail. These are the names: lattice gauge theory, renormalization group and ADS-CFT correspondent. These things we have already seen. We have also seen that how would you prepare for quantum field theory, which includes that you need to know the mathematics of classical part, you need to know the physics of classical part, you need to know the modern physics and modern mathematics along with the basic overview of particle physics, and we also need to know quantum field theory, which is the best book. And we are going ahead with this particular part. Earlier video we dealt with the classical part, but we are going ahead with the physics of the classical part because that is more important before we jump into the real mathematics of quantum field theory. And selecting the right book, yes, it is very crucial in understanding and what are the online resources, lectures, websites which we will eventually cover in this series, that what are the right resources in which you need to go through. We have also seen in the classical field theory, generally what happens is that we treat things as particles. So when we are dealing with particles, it is very easy because we can compute and find out the position, momentum, coordinates, etc. But the thing is that when there is a transition from particles into what we call fields, things become very different. I won't say difficult, it would become different. We have seen that, and we have seen that in the earlier video, that there is a conceptual foundation, that classical field theory is a conceptual framework, and such as electromagnetic field, gravitational, and it exists in and interact in the classical world. Mathematical tools are important because mathematical tools such as Lagrangian and Hamiltonian formulations are dealt with. Now from particles, once we go into fields, there is a complete paradigm shift, and why do we need? Well, that you can look up into the other part of the video, but the most important part before going ahead is that we are no more dealing with particles. So eventually all the frameworks, all the concepts, all the mathematics, all the measurements will now come into the area of fields. We have seen that this is one of the best book which we have been studying in the area of classical field theory. These are few of the quick reviews which shows Leonard Susskind's book is so famous and so beautiful. Now what we do is that we now come to what is called that which part of the classical mechanics is important. We know that there are a lot of things which are important in classical physics, but we need to segregate. We need to customize and divide it in blockwise, that which part of the classical physics mechanics is important. Coming into the next part of the video. The first thing which is very important is this one, and I will definitely prove you that why it is so. The Lagrangian and the Hamiltonian mechanics. Now if I take as a whole Lagrangian and Hamiltonian, and if I try to find out the reason why it is so important, the first reason would be this one. You see, Lagrangian mechanics actually provides an alternative, another way of formulating the classical mechanics. Now why it is so? So you see that in quantum field theory, the Lagrangian density instead of Lagrangian mechanics, it plays a very, very important role. Because why it is, we will soon become clear, but you need to understand that we are no more dealing with particles, we are dealing with fields. Fields are widespread over a huge area of space and time, and that is why we need to find out the density over that expanse, and that is why Lagrangian density is important. You see, I have underlined that in red, that the transition from Lagrangian mechanics, which deals with particles, to field theory actually involves extending Lagrangians to Lagrangian densities. Now the question is that how Lagrangian density is related to quantum field theory. So one part is clear, that Lagrangian mechanics instead of particles are now being extended to Lagrangian density, because it is all about fields which are spread over a wide area of space and time. The question rises that how Lagrangian density will be related to quantum field theory. Okay, let me give you a very quick explanation so things will become much more clearer. Now we know that the Lagrangian density is denoted by this L, which is a fundamental concept in classical field theory, and QFT. Now this is, we know it is an extension over the Lagrangian formalism. Now what we do is that if I take a given a Lagrangian, say for example L, and we know that we can calculate the action integral by using the integral sign of the Lagrangian followed by dt, then typically when we take this curly L, which is basically the Lagrangian density, then the action integral becomes this. So the action integral becomes this. So what we see, you see that the extra integral is just the spatial coordinates, that is x to the power 3. So what we have done from this equation is that we are trying to make a point that the Lagrangian is the integral of the Lagrangian density. That's it, nothing else. And in this way, there is a perfect analogy which shows between mass and density. So the Lagrangian density is nothing but it measures the distribution of the Lagrangian over the space. So it is the same Lagrangian, but you see it is now spread over a time. So we take the Lagrangian density over a space. But I think that this is not quite clear, isn't it? We need a little bit more explanation. Let us look into the next part of our video. Okay, so you see from here, if I take L as the Lagrangian density, the first thing is that we have already seen that it is the integral over the Lagrangian density over the space-time region. The second thing is that, this is important, the Lagrangian density is used to quantize the fields. And what do we mean by quantize? This means that the fields are treated as operators that obey the rules of quantum mechanics. We will come to this, what do we mean by operator and why do we need an operator? We will soon come to that. But understand that the Lagrangian density is changing the fields as now are treated as operators. Why? Because the field leads to prediction of new particles, the creation and annihilation operators. Thirdly, we have to remember that QFT is all about fields. That was what I was telling, spread over a space and time, and we are no more dealing with particles of any system. So if I take a kind of a generalized coordinate of f and k, etc., then what this shows is basically the kinetic energy. What this shows, the del mu, is the partial derivative with respect to space-time coordinate, because we all denote space-time by mu and in general relativity with mu and nu. And this Fi or Fj, which is again the generalized coordinate, we are requiring generalized coordinate because the Lagrangian mechanics is now spread over density. These are called interaction between fields. Don't worry, we will deal with this. What do we mean by interaction in the coming part? But this is how the Lagrangian density is spread over. And there are many types of Lagrangian density. This is just to show you how it looks when I integrate and make it over mu nu, that are the different indices of space and time. This is actually the Lagrangian density for an electromagnetic field. So the first part of classical mechanics, which should be absolutely clear before delving into the complexities of QFT, is that you need to understand Lagrangian, Hamiltonian, and how the Lagrangian action over principle is now spread over Lagrangian over density, Lagrangian density. Now the question from here which we can think, or you can think, is that all these are related to some kind of a similar manner, symmetry which is happening, because one part is getting extended to other. So there is a kind of a symmetry, but there is a change of the symmetry. Coming up into the next part of our video, we will deal with something very important which is called symmetry and Noether's theorem. Coming up into the next part of our video. Now see, the thing is that symmetry is a property of a system that does not change under certain transformations, obviously. And Noether's theorem states that every continuous symmetry of the action of a physical system has a corresponding conservation law. So in quantum field theory, these symmetries actually plays a very important role, and they can be used to simplify different kinds of equations of motion, to classify different types of particles. Let us see. Again, the question is that symmetry and Noether's theorem, why it is important? Here is the answer. So as I told you, symmetry is something which does not change under transformation, and they can be used to simplify the equations of motion to classify different types of particles and the interaction between particles and fields. So we need to understand Noether's theorem. The reason is that it can be used to relate the symmetries which we deal with quantum field theory. Also, this is important, that symmetries provide a framework for understanding how physical quantities behave under transformation. Obviously, because when you are moving from quantum mechanics to quantum field theory, there are a lot of transformations. But if this transformation creates an inherent change, that is a problem. So symmetries actually will provide that how physical quantities behave, and most importantly, the transformation leaves the equations of motion invariant. There is no change. The question is that we are talking of symmetry, symmetry, symmetry. What are those symmetries? Coming up, very important point into the next part of our video. So you see here, it is a basic definition of symmetry, and it simplifies the equations of motion to classify different types of particles and to understand the interaction between particles. Right. So first let us see what is called a continuous symmetry or Poisson symmetry. Now these are symmetries that do not change if you make any arbitrary transformation. And this is important because continuous symmetries in quantum field theories are called the Poisson symmetries, which are the symmetries of space and time. So translation, the laws of physics are invariant under translation of space-time. The rotational laws of physics are invariant under rotations. Lorentz transformation, a combination of transformations and rotation that maintains the invariance of the laws of physics under the change of the observer's velocity. Discrete symmetries, these are symmetries that only change under specific transformations. Parity symmetry, for example, a transformation that reverses spatial coordinates. Change conjugate symmetry, for example, the parity, it is called a transformation that exchanges particle with corresponding particles. Then there is a time reversal. It shows that a transformation that reverses the direction of the time. It is not always conserved in particle interactions. Then we have got internal symmetries. These internal symmetries are a class of symmetries that do not involve the space-time coordinate of particles. Instead, they are transformations that act solely of the internal degrees of freedom of the fields of particles with the theory. Now, what are those? For example, we have got isospin, an internal symmetry involving the transformation of particle states between different charge states. Then we have got a flavor symmetry. Similar to isospin, it is an internal symmetry that involves transformation among particles of different flavors. Then we have got a chiral symmetry, a symmetry that involves the handedness of chirality of particles, and it is relevant for massless fermions. Then we have got something which is called a supersymmetry. It is a theoretical symmetry that proposes a kind of a relationship between fermions and bosons, providing a solution to certain issues in particle physics which we are not dealing right now. But understand that SUSY, SUSY, or supersymmetry tells that each particle is paired with a supersymmetric particle. Then we have got a conformal symmetry, a symmetry that preserves angles but allows for scaling of distances, and it is relevant theory with conformal invariance, such as in the theories of critical phenomena. Now, all these symmetries are actually very integral, and the question now rises is that why should you study these? All those continuous, discrete, internal, the mathematical notations. Question is that in studying quantum field theory, we understood that symmetry is important because this would be used when there is a transformation, and Noether's theorem is one of them. It is a classical system. The question is that why should we study this? Let us understand into the next part of our video. So you see the continuous Poincare symmetry. It is important. Why? You can read the underlined red one. It leads to the conservation of momentum of energy. Then we have got the continuous, we have got a rotational energy. So rotational energy is important because it leads to the conservation of angular momentum. Then we have got parity. This is in quantum field theory, this symmetry can be important for some interaction. Then we have got discrete symmetries. This is important in quantum field theory because certain reactions and certain anti-reactions involving antimatter. This is very important. So you see, I have given just a few examples, otherwise the video will be too long, but these are important. We need to understand before we go into QFT, because each of them are I would say a very integral unit of QFT, and missing that would create a problem. So you see that finally we summarize that these symmetries are actually the building blocks of the universe, and they help us to understand how things move, how things interact, how things transform under different systems. And QFT is all about particles and the interaction, and we need to know the symmetries, otherwise we won't be able to understand that. The question now is that we understood about symmetry, we even understood that there is a link between QFT. Question is that why do we need to understand Noether's theorem and not any other theorem? Let us find it out in the next part of our video. So Noether's theorem, if I take in a figure, one is a symmetry and a conservation of law, that these things are very closely related to each other. How? For example, if we consider the translational symmetry we have just seen, this means that the laws of physics are the same at all times. According to Noether's theorem, this symmetry leads to the conservation of energy. Similarly, rotational symmetry in space leads to the conservation of angular momentum. Translational symmetry leads to the conservation of linear momentum, and gauge symmetry leads to the conservation of electric charge. So Noether's theorem, actually the link is that it helps us to comprehend how these symmetries actually lead to conservation laws. It also helps us to provide a rigorous foundation of the symmetric principles, and Noether's theorem actually has implication for the quantization of fields and quantum field theory, and it helps us to understand how certain quantities, I mean to say charge, currents, etc., will be conserved under the framework. So you see that there is a symmetry, a conservation of law, and this Noether's theorem actually helps us to comprehend, understand, and provide a rigorous understanding of the symmetric principles and how they are related to quantum field theory. Here is a quick summary. This is the mathematical underpinning that connects symmetries to, I would say, conservation laws, which plays a very vital information in understanding the different interaction of particles, and the mathematical formulation which we are heading to is the quantum field theory. Now, till now in the video, I think things are going fine. You have been able to understand symmetry, Noether's theorem, etc. But all this requires a kind of a I would say quantization. We just noted about quantization. What is that quantization and how do we do that? Does that quantization actually helps in understanding quantum field theory? This is coming up into the next part of our video. This is a very important concept, and I would request all of you to pay attention. This is called canonical quantization. Now first let us understand the meaning of this term canonical. Now it actually is a confirming a general rule. It is relating to a clergyman who is a canon or something related to the church or council. So in general what we can say is that canonical means something which is related to acceptable law or a procedure. So here it is, the definition. Canonical quantization is a procedure for quantizing a classical theory, but we will try to preserve the formal structure. That means from classical theory we are going to quantum mechanics, that is we are quantizing, but we will try to preserve the formal structure, which are symmetries, etc., to the greatest extent as much as it is possible. Now historically, if I say, this was not quite Werner Heisenberg's route to obtaining quantum mechanics. It is actually from this handsome gentleman in 1926, Paul Dirac, actually formulated this in his principle of quantum mechanics. This method was further used by Paul Dirac in the context of quantum field theory in his construction of what is called quantum electrodynamics. And this is known as the second quantization in the field theory. This is called the second quantization, and the first quantization actually involved the semi-classical quantization of a single particle through what is called the wave equation of psi, and that is what is called the quantization, first quantization. The first quantization is basically through the wave function, and the second quantization is what we are doing, that Paul Dirac's usage of quantization to formulate quantum field theory. Now we understood that quantization is a process in which the classical theory will be quantized, but we will preserve the formal structure. How do we do that? What does it mean to preserve the formal structure? Let us look into the next part of our video. So here is the answer. What we do is that we will replace all the classical observables, which we call observables, with certain quantum mechanical operators. This schematic diagram will give you an idea. You see, these are the observers: the position, momentum, kinetic energy, total energy, all this one, the left one, which I just underlined in red. And these are now being changed by what is called operators, that is quantum mechanical operators. What do I mean by that? If I generalized that observables becomes operators, then if we use Heisenberg's uncertainty principle in terms of classical way, it will tell that it is impossible to know both the position and momentum of the particle with perfect accuracy. But when it changes to quantum field theory, it will tell that it is impossible to both the value of field. We cannot know the value of the field and its momentum at the same time with perfect accuracy. So you see the transition of the particle now becoming a field. However, the observables are now changed into operators. Let me give you a very quick and a very easy mathematical example to understand that. So you see, to quantize the classical system, what we do is that we canonically conjugate variables become operators, which are denoted by a hat sign, and we replace all the Poisson brackets and replace by 1 by h bar times the commutator of these operators. So for example, this one we change it to this, then I take a generalized coordinate, we change it to this, and this one I change it to this. So what happens is that the operators are taken to act what we call linearly on vector space. Let us take an example. This is as you can understand, is a simple harmonic oscillator. Now if I start quantizing, which I have skipped over there, making the replacements, all both these hats, etc., this is what we will get. This is actually what we get final after quantizing and making the replacements. So you see, this is what I was stating. The operators are taken to act linearly on a vector space, and the vectors are basically now called states. And now this is often summarized, I can say a little bit technically, what we call this one. We replace all the Poisson brackets by commutators and put hat, a kind of a hat sign on everything, and this is the rule which works everywhere. Very simple rule. What we do is that we take the operators, and then what we do, we replace all the Poisson brackets with the hat one, and this actually operates in a very nice way. So this is, this is a very quick and a very simple, trivial understanding of how these operators, classical observables, are changed into operators, and how I am replacing all the Poisson brackets by commutators. The question is that, is there a step? What is the way? I have skipped certain steps. What are the ways in which we can find out the canonical quantization? Coming up into the next part of our video. So first we do is that we identify what are the variables that we are going to canonize, canonical variables. Second is that we promote them to variables of operators. Then we introduce commutation relations, and then we quantize the Hamiltonian, finally solving the Schrodinger equation. I know it is little bit mathematical, it is little bit technical. Don't worry, we will deal with this in the Poisson bracket section. So these are the steps: identify, promote, introduce, quantize, and solve the Schrodinger equation. This is the summary. So canonical quantization is actually a very powerful tool, and it is not but it also has limitations which should remember, and the limitation is that it can be difficult to apply when we are again dealing with degrees of freedom. And another limitation is that it does not always produce a consistent theory. But in spite of this, this is how we do the canonization, and that was Paul Dirac who first found out that. So we are going ahead with what are the parts that we need to understand in quantum, I would say classical mechanics. And one thing which we are still not explored is the field theory and what is called the classical field theory, coming up into the next part of our video. Now I'm not going to explain it much because this is already expanded quite a lot in my earlier video. You can go and look into part 1. I started with Landau-Lifshitz book. Then due to mixed reactions, I selected Leonard Suskind's book, which is a complete understanding, very easy, simple, and it is highly recommended as a first step to understand classical, I would say, classical field theory. Without classical field theory, obviously, we cannot go ahead in further understanding what we call quantum field theory. Now, the next question which arises is that what next? And we have dealt with what we call Hamiltonian equations and Poisson brackets. Let us look why it is very relevant to quantum field theory, coming up into the next part of our video. We will deal with Hamilton's equations and Poisson brackets in a very easy manner. So this is, you need to understand that when we are moving from classical field theory to quantum field theory, there is something which is called a transition. And this transition, I'm not going into the mathematics, which I will deal in a separate lecture. This transition is actually done by Hamilton's equation. What is those? Number one is that it actually establishes the connection between classical field theory and quantum field theory. One. Second is that it allows to formulate quantum field operators, because we just saw that the observables are changed into operators. And how do we do that? This is how we do that, using a Hamiltonian equation. And also these classical fields are actually being replaced by quantum field operators. So this is the importance and the link and the transition between classical field theory and quantum field theory. And we saw that it actually helps in canonical quantization. So Hamiltonian equation, I'm not going too far. This I think we have explained earlier. So in classical physics we take the total energy. Quantum physics also, it is denoted by the h bar, which we deal with h equals to t plus b. We just put the hats. This is again a canonization. So here you see this one when it is replaced with the Hamiltonian. So what it changes, that this changes to h operator and this kinetic energy is being changed into this. However, I would request to all of you, if you really want to know more about Hamiltonian equation, then what I would request, this is the potential energy. You can look into this one. This is a very important video, the relationship between Hamiltonian and Hermitian. It is there in my playlist, in my videos, Physics for Students. You can go ahead and check. Now, the Poisson bracket, if I take it quickly, is basically a mathematical concept which describes the time evolution of the system. I'm not going into details because it would demand a separate video. So if I take a kind of a generalized coordinate f, pq and gpq, then I can use this quantum, the Poisson bracket in order to replace that. Remember, this q and p can be dropped from the lower indices in order to make things clear. So in the context of the quantum field theory, what it is happening is that the Poisson brackets are just being replaced by commutator like this. And what we know is that in quantum theory, the field operators do not commute. And this is why the order in which the non-commutative behavior actually is something very fundamental feature of quantum mechanics. And this non-commutativity actually of the quantum operators is a key feature, and it allows to describe quantum fields and its particles, unlike classical mechanics, and further into quantum field theory. So this is actually the role of Hamilton's equation in terms of Poisson brackets, removing them, how we are replacing it with the quantum operator. So we understood the physics that is required. Now the question is that how do we study, and what are the books, what are the best suggestion of the books coming up into the next part of our video. So here we will know that we will study the physics part, right? And then we are coming to the mathematics later. So how much physics we should study and what are the books to study? Now when we say, I say how much physics, do I mean that you don't have to study the physics for the rest? No. What I'm trying to say is that what are the areas in which you need to emphasize and understand and spend time more? The first thing would be special theory of relativity. Obviously. And now I am dividing special relativity in two parts. The first is that you need to get a basic idea of all the concepts, and second is that you need to specialize on certain relativistic parts, because your aim is to learn quantum field theory. So first we will see which books gives the overall idea of special relativity. So this one I have recommended earlier by Farooq Rahman. This is a wonderful book on special relativity. It deals with pre-relativity, Michelson-Morley, Galilean transformation, Lorentz and everything. Then it goes into the geometric interpretation of space-time, relativistic velocities, etc. I'm not giving too much of details because the time is already quite long enough for this video. But this is a book which is going to give you a complete understanding of special relativity with all the aspects that is required to understand. Mass relativity, relativistic dynamics, photons, then the transformation for charge density, for current, for vector, everything. So first, for the essential part of special relativity to be learned, this is the book which will give you much details. Now this book is the second one, which I would request you that this is a specialization. Now see, the customer reviews from Amazon is more or less okay. Why I'm selecting is that the main target is basically the relativistic Maxwell's equation, which is more in this book, and obviously it leads to quantum mechanics unification, because quantum field theory is ultimately a unification of classical mechanics, special relativity and quantum mechanics. So this book, as I will show you what are the contents, is a very good book because this is much more I would say specialized to relativistic mechanics and Maxwell's equation. So you see it starts with relativistic kinematics, relativistic dynamics, Maxwell's equation. So that is why I told I will take two approaches. This is the second one which talks of the special relativity in relation to Maxwell's equation. Very important, otherwise the concept of quantum field theory won't be clear. The next book would be obviously Special Relativity and Classical Field Theory. I have already shown you the wonderful and beautiful reviews which have been shared. So obviously this is the must book. Now you see, if I take the content of the book, it's not a very fat book by Professor Susskind, but the things which are important are this one. One, classical field theory, you need to read it very minutely. Second would be the fundamental principles and gauge invariance. And the third and fourth would be Maxwell from Lagrange, as Lagrangian and Hamiltonian is very important, and the fields and classical mechanics. So this is a complete easy understanding, easy as simple, but remember 1, 2, 3, 4, those I have underlined. These 4 areas would be something which you need to, I would say, concentrate more. This is something which is being ignored by most of the students, which is called wave mechanics. This part is important. Why? Because the study of waves is important in quantum physics, and because waves actually form the fundamental block of quantum world, and from there we move into wave function, and then further from wave function to quantum field theory. This is very important. You cannot ignore the basic of concept of waves. So wave particle duality, wave function, wave interference, wave packets. This is very central, very important. Because you're going into QFT, do not ignore these basic parts. Otherwise later you might face a problem. What is the best book for understanding waves? The answer is this. Daniel Fleisch and Laura Kinman's book, Student's Guide to Study Wave. I have read it. One of the best, I would say, contains all fundamental concepts. These are some of the table of contents. It is not a very fat book. It contains examples, very, very easy. Wave fundamentals, wave equation, wave components, and so on. Schrodinger equation, very important in order to understand the basics of quantum physics and later go to quantum field theory. What is the best book of Schrodinger equation? This one, Daniel A. Fleisch, A Student's Guide to Schrodinger Equation. Very simple, and it assumes nothing. It will teach you right from the beginning. So these are some of the table of contents. Again, it is not a very fat book. It is quite easy. It starts from vectors. It builds your concepts, operations, eigenfunctions, Schrodinger equation, and this is a not very costly book also. You can find it at Amazon. This is a must-read book. Coming up next would be Fourier transform, and there are around this is actually giving you a basic idea, which you know that Fourier transform actually breaks down a single signal into individual frequencies. If I get a music, I can divide it into this and further into this. So Fourier transform actually decomposes into constituent nodes for further study. So for example, it's just like a vector which we can divide it into small parts and constitutes the long blue vector. We can divide a kind of a frequency 5f into small frequencies like 3 frequency and then 2 frequency, and then we can add it up. So this is the role of Fourier transform. What it does, it breaks down and then it adds up so that it becomes easy to study. And this is my recommendation, that please look into my video Uncertainty Principle and Fourier transform. This is very important. I have taken a deep dive in establishing the link between Fourier transform and uncertainty principle and remove some of the misconceptions. So there are quite a number of books. This book, there are 4 books which I would recommend on Fourier transform, but the first book would be this one and its application. Second one would be A Guide to Distribution of Fourier Transform. Third would be this one, A Student's Guide to Fourier Transform. And fourth would be Fourier Analysis and its application. You can pick up any one of these books. Each of them are quite good. The next one and the last one would be the Lagrangian and Hamiltonian. Huge number of books are available in the market. However, I have selected this one. A Student's Guide to Lagrangian and Hamiltonian by Patrick Hamill. It is an absolutely wonderful book. Again, assumes nothing and it starts right from the beginning. Fundamental concept, Lagrangian mechanics, Newton's laws of motion, etc. Then it further goes into calculus of variations, etc., Hamiltonian mechanics, and so on. You can see further that it covers of Hamiltonian Jacobi theorem. This is very important quantum field theory, and I will cover up in the next part of our video. And this is, I can say, goes into the fundamentals. It takes the calculus of variations and then Lagrangian and Hamiltonian mechanics, and most importantly Hamilton and Jacobi theorem. This is important. Why it is important, I will explain it in the next part of my video. So this is a kind of an overall understanding of the physics, the internals, the technicals, and the best books to read. However, in the next part of the video, I will be dealing with something more. I will be starting with areas to learn in Noether's theorem and what is the best book for that. Then I will come to the quantum mechanics. Quite a large number of books are available, but which book you will select and which part of quantum mechanics is very relevant to quantum field theory, you need to read, but you need to emphasize on certain parts. Thermodynamics and particle physics, what are the books, how will you read, and what are the mathematical prerequisites for quantum field theory. So this is again will be part 3, because I am taking a step-by-step, baby-step approach in order to learn and make you understand about quantum field theory. So thank you very much for watching this video. If you have really liked, hit on the subscribe button and click on the bell icon to get all the notification for Physics for Students. This is my email ID and this is my other channel on general theory of relativity, and you can follow me further on my Facebook, LinkedIn, Instagram and Twitter accounts. Thank you very much for watching this video, and please do let me know how do you like the video in the comment section. I will wait for that. And coming up soon is the part 3 of quantum field theory, how to learn, so that you get a comprehensive, detailed and a step-by-step understanding. Thank you very much, and may the good Lord be with you.